Hello everyone. I would like to thank you all for joining us today. I hope you all are well today. My name is Aparna Haldar and I'm part of the community outreach team at Payatu. Before we get started, I would like to briefly introduce Payatu. Payatu is a research-powered cybersecurity consulting company with a track record of over a decade. Payatu has over 4 dozen CVs and counting. We collaborate with customers in 20 plus countries globally. This was all about Payatu. Coming to our guest speaker, today we have with us Bartek, wherein he'll talk about the fundamentals of fault injection and impart his knowledge and expertise on the subject. Bartek is the Vice President Sales Products at Riscure. Riscure is a committed team of security experts to guide their customers through the security challenges in connected device security. They provide services like side channel analysis, fault injection, connected device architecture, and software analysis. Since 2020, he has managed all tools-related sales activities worldwide with his team. You can learn more about him on this slide. Before I hand it over to Bartek, I request you all to follow a few housekeeping tips. Please be on mute. If you have a question, you can write it in the box. We'll answer the questions during the intervals or at the end of the webinar. We will be releasing the recording of the webinar on our LinkedIn page. So make sure you're following Payatu. If you're not following the page, check the link in the chat box. You will be directed towards Payatu's LinkedIn page. Without further ado, let's get started. Bartek, over to you.
Thank you very much. Thank you very much for the introduction, and hello everybody. Let me start the screen sharing, and let me ask you if you can see my screen now.
Yes, Bartek, it's with.
Perfect. So welcome everybody. I think I have a little bit less than an hour to talk about. If I look at the camera now, I look a bit like Princess Leia because I have a headset on, but I hope that is okay. Let me see if I can start this to the next slide. Yes, so a year ago, or 2 years ago actually, can people hear me? I hear some other people talking. Maybe we can mute.
Participants, I request you all to please mute your devices.
Yeah, that would be nice to mute. 2 years ago, the pandemic started. I think it's almost to the.
Bartek, I think you've gone on mute. Can you please unmute yourself?
Okay.
Yeah.
Now I hope everybody's on mute, and I'll be on mute. I hope you can all hear me. So 2 years ago, the pandemic started, and I was actually flying from China to Holland when they started closing down on Chinese New Year. So we were sitting at home, and I thought, let's do something fun. The kids were at home, so I actually took a. I hope you can see it now. We bought a bug zapper, so something that kills flies, that generates electricity, and you can kill the bugs. And we opened it, and we removed the top part, and we added a coil. So we created a coil, and here what you see here is there's actually also a little bit. I don't know, you cannot hear it, but we created a bit of a current here. The videos don't want to start, so that's too bad. I don't know why, but this was an example of how we were actually glitching this this scale, and so this was a fun project to do, and I would recommend everybody to do that with your son if you like. The video is not starting, but I will share the videos later. You can see the videos here if you search. This is also used in real life. People make their own glitchers to hack, for example, slot machines. So this is an example that someone hacks the coin reader and glitches it to generate money, which I think nowadays I think is environmentally more friendly and cheaper than generating your own Bitcoins. So before we talk about fault injection, let's talk about side channel. I think a lot of people already know side channels in this field. Side channels are there known maybe more than 20, 30 years. How we define it, it's an unintended interface that leaks information. And typically, if we talk about chips or embedded systems, we think about physical properties, current, power consumption, current that goes through wire leaks, an EM field or generates an EM field that we can measure. But it can be temperature, it can be timing, it can be a clock that fluctuates, etc. So a lot of those physical properties, that's what we call unintended interfaces that are there, not by design. Yeah, in the Netherlands, we look at side channels, marijuana, so we can sell weed here, but the question is, where do we grow it? Either we buy it from another country or people grow it at home. And if it snows, the Dutch police flies over the roofs and looks at certain houses that are somehow leaking information. This person here on the right in his house leaks information that at least he's heating up something. And to grow marijuana, you need lamps. So think about, how would you mitigate this? You are the hacker, or you are the grower. How would you mitigate this? So if you have an answer, please write it down in the chat box. Happy to look at it and discuss it later. So from side channel to fault injection, we talked about these physical properties, and actually we use the same properties, but now the other way around. We are using voltage, current, or electromagnetic, and even laser light to change the internal state of a IC or an integrated circuit, a chip, or whatever you like to call it. So we want to change the internal voltages, the current, the charges, in order to change device behavior, data, and operations. So fault injection is a physical attack, mainly focused on the logic. In summary, side channel, I would say it's like a psychiatrist that interrogates you without being physical, non-invasive. He asks questions and hopefully you will leak some information that you didn't want to. Fault injection is more an interrogation by Batman who beats the hell out of Joker to get information out of him. So he wants the same thing, but in a different way. So if we look at fault injection, we have a chip that has a certain safe operation area, let's say between -8, well, 1.8, sorry, 1.8 and 5.5 volts. But what will happen if I would start operating this chip outside of this normal operation area? So for example, if we would go higher than 5.5 volts, probably it will generate too much heat and the chip will start burning, smelling, smoking. Maybe you've seen that before, when we turn on the wrong power supply in the wrong target. If we go lower, probably the target does nothing. So it will go to sleep or will not even boot at all. So what we do now with glitching, we want to go slightly above this threshold or slightly below this threshold. And this is what we would call a glitch. So we don't want to go too low, too long, that it dies or sleeps, but just for a second at a certain time for a few nanosecond, milliseconds. Another way of looking at it is we supply a certain voltage to a chip or target, and at a certain moment of time, we will dip the power. We dip the power that it goes below a threshold logic. A transistor or a gate will flip below a certain value, and that is what we're trying to reach. So these are a few ways to look at how we do the physical part of the glitch. So when we look at the process of glitching, we need to define normal behavior. We need to set up what are we considering as normal output. And here are some 3 examples that I made for secure boot, for example. If we want to boot up a device with some malicious firmware, the normal behavior is that it will not boot. It will deny loading this, let's say, malicious firmware to the device. It will say no, or it will give me some output saying you cannot go in. That is normal. Or we encrypt something with a key and we get a certain ciphertext. So every time, very deterministic, every time we put in the same input, we get the same output. Or verification of a random pin, the device will not grant us access. So that is what we would call normal behavior. And that is the first process we need to set up with any process of glitching that we want to do. We typically indicate it with a green light. And I'm using the metaphor of traffic lights. Green means, in this case, normal. So now we're going to apply a glitch. For example, we want to inject a fault in the firmware verification. So the moment that he's verifying the firmware, we want a glitch. Or during the encryption, we want to corrupt the encryption, typically the last round of an encryption algorithm, to corrupt it in order to get the key out. Or we want to disrupt the comparison of the PIN code verification. And so that is what we are aiming at. So what we're going to do, we're now going to do a repeated process. We're going to let the system do the normal behavior repeatedly. And in a certain amount of time, we're trying to glitch. And we look at the output. The output can either be normal, green. If we're unlucky, or maybe lucky, it gives us also some information. The system dies. Because we glitched it, it went into a state that it can either do nothing, or it really dies, it stopped working. That is quite extreme, but happens also a lot with fault injection. Or it goes into a routine that it should not supposed to go in, and it cannot operate further. Or it goes into what we would call the red light, is it dumped some memory. It went into some call that would give us information, or it went into a state that is what we were looking for. And so based on the output, we define, let's say, the coloring and the expected effect that we're looking for. So the attacks can occur, and I already gave it away a little bit on a few physical properties, but we try to attack either through clock. For this, we need some kind of glitch generator, something that accurately can create a glitch in different ways, high, up, long, wide, on the clock line. We use the same glitch generator typically to also attack the VCC, so the power, or to manipulate the power. We can look at EM, electromagnetic, that is on top of a package. In this case, we also add a spatial component. Compared to a house, if we look at clock or VCC, that is something your front door, we're attacking the front door. Typically that is well protected. And now with EM, we're going to scan the whole house and we're going to find if something is open. So for that, we need some kind of probe that is connected to your glitch generator. Another way is to use light and laser. And that is basically, we need to remove something. We need to break in the glass in a house and try to then get in. And that is laser. We need to decap a chip, typically get to we need to remove the substrate or the shielding or the packaging in order to have effect with the light. Another way is temperature, but that is something we do use or we can play with, but that is something not that we use currently as a glitch. It is something, yes, to lower countermeasures. Maybe sometimes certain countermeasures don't work if you go out of the operating spec of a chip, but that is something that is very hard to control in, let's say, nanosecond precision. It's very hard to get the temperature down in a few nanoseconds of a whole device to glitch it. So if we do the attack, we do the glitch, there are certain outcomes that we can expect. Either it's a transient, so it happens only once during the perturbation or the glitching. Perturbation is another word of glitching. It can have a temporal effect. So as long as the device doesn't boot, a certain value is changed or condition is changed. Or we can have a permanent result that, that even after rebooting the device, it is still in a certain set. We have examples that we glitch something and maybe we touched on the views or a memory or a ROM value that actually the device kept on outputting the firmware or the boot ROM every time we rebooted. In general, we say fault injection is finding a needle in a haystack. It is not easy. And for this, you need, I would say, good tooling, good knowledge, good understanding of different fields of knowledge from electrical engineering, computer science, cryptography. But if you all mix that together and you find the fault, typically it's quite easy to reproduce the attack. So it is quite easy to find that needle very quickly again in that haystack. So what are we trying to do with faults? And what can you do with faults? We already established what we want to do, but what can you do? So we can do, typically we say two things. We can either change operations, skip instructions to, for example, reverse life cycle, make sure that a counter is not counted or that a verification is bypassed. Or we can change data. We can zeroize something or maybe change a randomness to something that is more predictable. We can do a differential fault analysis attack, a DFA, that is manipulating an encryption, and then based on multiple of these manipulated encryptions, we can derive mathematically the key. So those are the two things, or the two fault models that we typically look at. There's maybe a third one, but that is something maybe more advanced, and I will update that later. That is something that we're discussing with our friends from Realize, but that is for another topic. What I wanted to highlight here, that fault injection has a bigger attack surface than side channel. We started with side channel, and many people know side channel, which we attack encryptions. We look at how an encryption could potentially leak a key or an implementation of an encryption. But with fault injection, we can do more. We can attack the encryption, but also attack loops or checks, etc. So I would say the attack surface of fault injection is much bigger than faults. If we look at a chip, we have different levels of implementation. That would be the OC model. We talked about fault injection as a physical attack. We look at the physics, we can change bits. We have different attacks, we can attack ROM and registers. But on top of it, something like opcode is running. On top of that is assembly. On top of that is general code. So what we are actually attacking, sometimes it's a bit unclear. Where is the vulnerability happening? We know we attack a certain condition in time, but where does it go wrong is sometimes hard to say. To show that a little bit, I have here a code review and a code example. Typically, we show this in a live session, so we can have a little bit more attention here, but I would encourage you also to re-look at these slides and maybe look for yourself. I have a pin check password verification algorithm in the next slide where, I would like you to find a potential fault, either by data, looking at changing the data from 1 to 0, 0 to 1, or any other value, or skipping a line, or skipping an instruction. So this is the algorithm. I will give you a little bit of time to look at it. What you see, we're declaring a few variables. Charge OK, 0, authenticated. We define the location where we can get the input that we're checking. And then we do a loop. We loop through 4 bytes where we compare the buffer that we just declared here, compared with a stored password location. And then if if the charge OK is incremented up to 4, we can authenticate that this password or this input buffer is equal to the password that was set. If not, then we'll go into a different output saying this is wrong. So here we would establish, if we would a random input, we would establish a green expected behavior is that we end up continuously in this 69 and 86 output value going out. I hope you already had time to look at it. But there's actually a lot of location in this code that we can glitch. For example, potentially we would be able, luckily, to change the value from 0 to 4. So this means, doesn't matter if we have a random value or 0, we will always get to a 4. Or maybe we change the authenticate to 1. This means even if we don't get here, the authenticated is set to 1, helping other functions later in the code to maybe reveal some code. Maybe we can change the values of the loop. So we can iterate longer in order to be more lucky to get to 4. We can change the pointer to password. We can increase the value of charge OK during operation, or we can skip these instructions, etc. There's actually a lot of, and maybe there's even other ones that you can find here. So this implementation, from a fault injection point of view, would not be very secure. And it gets worse. We talked about, this is the high-level code C, but what about compiling it? We compile it, it goes to assembly, and actually in assembly, we generate even more lines of potential vulnerabilities, and maybe they're executed in the same time, but we can maybe change registers or still have a comparison that we can skip here. So the message here is, it is very important to not only focus on the code that you're developing, but also look at what is the output, or how is the compiler set? Is the compiler optimizing? As we know, a lot of secure boot is actually also coded just in assembly because of security and more control reasons. So a little bit of promotion, but this is an open source tool. If you want to go to github.com/riscure we have a very nice simulator that looks at these two fault models. This is a secure boot that you can download, and it implements a normal behavior secure boot. And we're going to glitch and simulate time and running the code with random value. And actually, if you do nothing, you have 245 glitches. If I'm correct, maybe we change it a little bit. Your goal is to change the code in C. How much time, that's interesting, with how many changes, how little changes, you are able to get this to 0. So let me know afterwards or later how successful you were with this. So this was a lot of introduction about fault injection. I hope this gives you a little bit of insight on what is a fault, what does it do, what can you do with it. Let's look a bit at embedded systems in general. We see that many embedded devices implement a lot of security features, which things are like secure boot, secure code updates, like over-the-air updates, encryption, authentication, secure communication, and higher level, there's even policies. There's this detection and reaction mechanisms included. I would say that's awesome. That's super, super good. Unmute. So I'm unmuted. Am I unmuted again, I hope?
Yes, you're audible.
Cool. So I think it's great that people look at security and implement a lot of security features. And they do that because there's a lot of hacking going on. And if I would look at hacking and people trying to circumvent things, logical attacks are the #1 threat of any embedded system. Because you need little tooling, you can just start probing or fuzzing the interfaces. There's a lot of simple tools that you can use. So that is the main focus. And that's why many developers focus on implementing some software countermeasures as discussed. There's secure coding practices. There's even some static coding analysis tools, fuzzing, etc. So that's all great. But what happens if we mitigate things on the software side? What will hackers do? They go for what we would call the low-hanging fruit, the path of least resistance. And I think that hackers are going to explore more hardware attack tools that are also now getting more accessible. So I think the next logical attack, with brackets or quotes, is fault injection. So the threat of fault injection is we can actually create logical attacks. We can create buffer overflows. One fault to rule them all. One fault is needed to dump a firmware or bypass a secure boot. Every unprotected IC is vulnerable to fault injection attack. By definition, ICs are not mitigating fault injections. Maybe they're not all of them need to do that. And as already said, fault injection has a greater attack surface than side channel analysis. So the real threat, so we have some practical examples. I don't think Chip Whisperer is a threat, but hackers and hobbyists have access to Chip Whisperer, a great tool to play with. They typically buy that and modify it and add their own knowledge on top of that to start hacking. It lowers the bar now for hackers to hack. And here are some examples. Ivanlu, PlayStation, we see Truststone, we see switches, and last year, Apple AirTags. And this year, actually, Tracer Wallet, actually that was hacked already before, a very nice video. I'll talk about that later also. But we already know hacking for the past. We know that hacking has been used for many, many years. Think about the Xbox 360 glitch chip that was out there that you could buy. Automotive hacking that I will talk about later, secure boot, etc. You know, over the last 6-7 years, we've seen an increase in fault injection hacking, and I think mainly also through the attention of Chip Whisperer. This is a video that will also not run. I cannot show the whole video, but there's a link here. This is a very nice example of how maybe an innocent device is glitched, and where through glitching they have access to the debug port. They dump the firmware. They then find a software vulnerability that they can exploit and load their own URL to use with the AirTags. This came out, I think last week or a few days ago. Joe Grant showed how he got 2 million out of this Treasure One hardware wallet. It took him 3 months, but he succeeded. So he earned $2 million. I think that's awesome. Maybe for those who don't know, there's already a lot of standards in the world that look at fault injection attack. And I think smart cards are a good example. Smart cards are there for 25, 30 years. Based on common criteria, EM-VICO, there's a lot of attention to fault injection attack. Not only power, EM, and laser, but even double laser attacks are considered. And for me also, I see smart cards as high-end security targets compared to all other devices that are out there. Set-top boxes, traditionally, a lot of hacking was going on there, satellite boxes and eventually routers, etc., where initially it was smart card and moved to system on chips that run encryption algorithms and advanced key algorithms there. Although that is now moving to software also. Payment terminals, they consider PCI, PTS testing, non-invasive fault injection attacks. So that is considered. The automotive industry is moving towards more security, but this is a beast, a very slow moving party that started with ISO 26262. Safety, some people consider safety the same thing as security. We see new standards popping up like ISO 21434. There's still a lot of discussion, what is fault injection? Is it an intended glitch or an unintended glitch? Is that different? Is that the same? So we're still not there yet, but slowly we're moving to more security because an automotive as a car is changing as a non-connected device to a fully connected device. Most of you probably know CVEs, CWEs, MITRE. They have a list of vulnerabilities, and also they consider fault injection. That's a countermeasure that should be considered. And if you don't do that, it's seen as a hardware design weakness. There's already 6 examples in the CWE that talk about fault injection in general. So that is something you can refer to. Maybe you don't know Global Platform, but that is an organization that looks at security also for mobile payment and mobility. And they create profiles for other parties to look at, for example, trusted execution environments, which are now used in many industries. And trusted execution environments look at side channel, but also fault injection. So it's a lot of talk, just to give you a little bit of insight of where already a lot of devices are actually tested against fault injection. I would like to show you an example that we did a few years ago on the UDS. UDS is a Unified Diagnostic Service that is implemented in many car ECUs. ECUs is a fancy word for a system on chip or device in a car that's typically shielded or boxed in, that is rigid and rugged because it has to work for at least 15 years. There's these car units that, for example, store information of the mileage that you have, and you don't want to read information out of them. So if I want to have access as a client, it's here on the left, and I want to talk to the ECU, I want to read out memory, I want to do something, there's a protection mechanism, which in cryptographic terms we call a challenge response. So basically here, me as a client, I'm requesting a challenge. The ECU will create a challenge, which here is called a seed. In the meantime, it will also compute the seed with a key. In general, what we see is an XOR, so not a fancy algorithm here. It will send the seed/challenge to me. I can calculate using a key that I should know in order to get access, and I'll send this key with computed the seed to get verified. And if we have the same output, the system will verify me and give me access or not. And so the normal behavior, if I have a random key or I don't know the key, I don't know the algorithm, I would send a random value V and the system will respond with no verification. And this is probably the algorithm that they're using to verify this system. So think about where should I glitch? And you probably, after the story already before, you know, you would like to, for example, glitch here. You could also do side channel fault injection in the key calculation, but we decided let's try our luck here and try to glitch this authentication mechanism of verification. As already said, safety is not equal to security, and we will show you why. So here we have the 3 lines. We have a trigger line, so we're going to create a trigger after, or sorry, just before we send the key, or we send the key command. So here we have the CAN bus, and we send the command, and just before sending the key, we'll generate a trigger in order for us to generate a glitch. So we want to generate a glitch, so we set the glitch voltage at a certain value, and then we glitch. If we're lucky, we get a response, and that is what we look at. What kind of response do we get? So now we have a few parameters that we can play with. We can look at the glitch delay. We can look, if we zoom in, at the glitch voltage, so how deep are we glitching, and the glitch duration. So we have established a time base, and we have 3 variables that we can play with. And this is something we're going to iterate. We're going to send this command, wait for the response, and see what happens. And based on that, we either reset the device or we run this request again and vary the 3 variables. For this, this is our system, and we generate what I call a 1D output. We get a table of horizontal inputs where you see the glitch delay, glitch duration, glitch voltage, and the output command. And based on this command, we give it a value, a red, green, or orange, the traffic light that we had. But let's plot this 1D value to a 2D representation. So that's something a bit nicer for the eye and a bit nicer for me as a human to interpret. So what we see here, we have the glitch voltage set against the x-axis, and the y-axis is the glitch duration. And you see here on the right side, we see some kind of, curve that on the bottom half, we see the normal expectation. So the output that we're expecting. On the left side, the yellow, we see the muted ones, the ones that did not give, or the system halted, and we had to either reset or hard or soft. And what you typically see, and it is a lot of behavior that we see, is typically on the borderlines between muting and normal behavior, we get sometimes the glitches. And this is something that we were looking for. So this is the graph that you would like to see, and these are the things that give us success. So in real life, what we did, and happy to share you the paper, we really bought some real instrument clusters from different cars, and we were trying to dump the code. What we did, we started to read memory, and because that was limited to a few bytes, what we did, we started glitching until we were successful. Top of my head said 1 in 100 attempts we were successful, and we were able to dump a few bytes, and then we would iterate to the next address, etc. So that's why it took us 3 days to get 512 kilobyte and 2 days to get 3 megabyte of flash code. So we used multiple glitching attempts and attacks, and based on a certain probability, we could scan through the whole address. Then put it into IDA Pro and reverse engineer, and we were able to get the UDS keys and basically now have root access to all these ECUs and do everything that we want. So this was a simple example how we showed to the automotive industry that, we know that you test one of the standards called ASIL-D. It's the highest standard against safety. That safety is something else, and fault injection in automotive is something else than the way we look at fault injection in security. So to conclude, fault injection is a physical attack on the logic. Fault injection is finding a needle in a haystack, but if you know where, it is easy to find the needle back. Fault injection has a bigger attack surface and side channel, and it's not that hard. It's as simple as understanding a traffic light. There is more. Countermeasures. As said, I see fault injection as the next logical attack. Many, but not all, fault injections can be mitigated in software. It's the way you program, the way you make your software and your code. Here we have a paper, actually we have 11 different ways to classify or how you can create countermeasures, like a double check, avoid low Hamming weights. You don't want to have booleans and flags because those are bits that you can flip with one bit, and you can rule them all, etc. There's many other ways to help you out. And combining these countermeasures, I believe you're already strong, mitigated against fault injection attacks. There's even one more thing. What we see for the future is the shift to the left. What we've seen, like with Chip Whisperer and the tools that we make and others, there's a lot of attention on silicon, peri-silicon, on-silicon testing, composite, software and hardware. But we're now moving to more source code analysis, where we see that the current source code analysis tools do not look at fault injection at all, but there are solutions for that. But either passive, but also dynamic, or static and dynamic with simulation. And we also look at pre-silicon. We think that in pre-silicon on hardware, we can also find vulnerabilities, which gives you more assurance when you go to a real chip. With side channel, we already have for many years TVLA, a metric to measure how strong a side channel analysis implementation is. That metric is not there for fault injection. We are on the verge of releasing a fault injection resistance measure, firm. Not for everything, we have certain classifications, but we think we can create a TVLA for fault injection, a fault injection resistance measures firm that we can quantify your resistance, which already in early stage on development can help you to guide you. Am I doing things right? Or should I change my countermeasures? And yes, we see also deep learning or AI being more implemented in fault injection. For example, tuning of parameters. So tuning your FI parameters that can be done automated. One more thing. I think most of you, I assume, a lot of you have not that much experience with side channel fault injection. So I would say try the fault injection simulator. You can download it, GitHub, play with it. Maybe make your own tool. For $60, you could actually already have a small oscilloscope, a resistor, open source tooling, and you can already do some side channel and a bit of glitching. There's of course Chip Whisperer, there's $300. There's a lot of open source tooling. For example, we have Jilska, or buy a book. Recently, Colin O'Flynn, Chip Whisperer, and Jasper van Woudenberg, CTO of Riscure North America, wrote a very nice book about hardware hacking. So I would recommend to buy that one or borrow it from someone who already has it. And if you want to know more, we promote fault injection. I have it here on my, we love Finland also, definitely, but we love .fi. We love fault injection. And we have a lot of videos explaining and helping you to understand fault injection. So we love FI. I am at the end of my presentation. I think I'm well in time. We are Riscure. We already have experience in fault injection for 20 years, and we are at least 15 years experts in fault injection. So are there any questions? Let's see, I see something maybe in the chat. Let me open up my chat session here. And I see one question. Could you please advise whether most of the side channel logical faults are local exploitation than remote code execution? Yes, thank you for your question. Yeah, I think in general, with everything that we do here, we talk about physical attack. We need to have access to the device. I do think that hardware attacks are scalable and not the attack itself, but what we see is that fault injection or side channel is peeling off an onion. You have an onion that has different layers, and we are peeling off something that we could not normally have access to. And maybe one example is the switch, the NVIDIA Tegra X1 and X2 have been glitched, and that device has been glitched one time by one guy that was able to dump the boot ROM, then using IDA to reverse and find a logical vulnerability that he was normally not able to find, and actually made 30 million switches, and now later maybe 100 million now switches forever being vulnerable to this exploit, which will be hard to mitigate in software. So what we talk about is local, which enables you to do scalable remote attacks. Hope that answers your questions. Yeah, I have Martin. How do you set the optimal trigger for clock voltage fault detection on how do you determine the correct trigger timing? Is there a procedure, good documentation on this? Yeah, maybe I would say probably the hardware hacking book that was just recently released. I would say that gives you a lot of more insight how to do fault injection or side channel or the timing. Timing is key. As said, it is searching for a needle in a haystack. There's a lot of variables. Timing, when to do a glitch, how low. A lot is trial and error. So is there good behavior? Yes, there is a good pattern. You need to find a trigger. You need to have good communication back. You need to, I would say, have good timing, which comes with hardware that you trust. A lot of hardware has jitter, and you can have luck, and be lucky and have a hit at this in the first trial that you do. But typically, you want to have good equipment that helps you to have more accurate timing. Let's see. Yeah, we have training on this. A lot of training. We explain to you with some basic targets that we have. One of the targets is Payatu, and soon we have a Riscure berry that we have. We made our own Riscure berry or Raspberry Pi, and that's where we also have a lot of nice attacks. So yeah, do a training. I think also our side channel voltage injection training is online available. So please have a look there. And I think also Colin has a public training, so maybe that's also something to look for. Let's see, I'm trying to scroll down. So I'm going to Hadi. Very informative, thank you. Can any type FI go undetected by the user? Let me see how I interpret that question. FI attack undetected by the user. Yeah, maybe different ways to look at it. So theoretically, I could steal a target from someone and do side channel on it. It will be non-invasive. I will not manipulate the device. So it could be that I can find the key and give the target back. With fault injection, you have a higher probability that you will be detected. Typically, a lot of targets are broken. A way of how people circumvent, and for example, with Joe Grant's video, you see that what they do, and this happens also in forensic, you take the same device and you experiment first. You find a vulnerability in fault that is more certain for you. Maybe 100%, 90% that gives you assurance that you will not break the device. And within only a few glitches, you will be able to glitch it and then apply it. So look at the video of Joe Grant. He applies his attack after 3 months of experimenting on one sample that he cannot break. Let's see, for FI, we need to know the source code, right? No, for FI, you can do, there's a lot of black box attack. So mainly it's black box. If we want to look at source code fault injection, yes, we need to do source code and we need to look at source code. But in general, fault injection is done on a black box attack. What we need to do is reverse engineering. We need to understand what's happening. So that's why I think you need to read the data sheet. You need to look at the signal. So you need to understand with the scope, what is happening. If I boot a device, a booting, maybe it's somewhat described how the boot process is of a system. But in general, you probably know how a boot sequence goes. It is somewhere storage is encrypted. So if we look at the sequence, if we look at with side channel, we measure the output, we see maybe nothing, we see the booting up, and suddenly we see some kind of signal increase, and then lowering, and then maybe more. So maybe some key is loaded. Maybe next step, there's a longer process, you see, hey, wait, there is some kind of verification going on maybe. So these are things that you would need to have to do in order to do fault injection or side channel attack. A bit of reverse engineering. Atit, you have a question. I've been great that you've been using Risk Inspector. Is there equipment or tooling already available for EM-based fault injection to test embedded systems? Yeah, definitely. I think Chip Whisperer has the Chip Shouter. There's also Langer. I'm talking about my competitors. But also we have EM equipment with many different probe tips. And our devices are quite accurate in timing. We also have different tips. And soon, actually, we'll have a new EM probe where you can actually do EM glitching and measuring, same location. So that's something that we are having. And all our equipment is suitable for embedded systems, definitely. The main difference from smart cards to embedded is communication. So smart cards is easy, connect. So maybe I assume you're using smart cards, but if you want to go to embedded, you probably need something to control it, some kind of I/O device. For us, we use a spider. So Martin, what chippers or hardware or other tools would you recommend for a beginner to get started? Yeah, I think I promoted Chip Whisperer a lot. Yeah, it is relatively affordable for a few $100s, or maybe you can get the schematics and make your own Chip Whisperer with components. There's even a light version coming out by that. As said, there's also in the slide you see how you can use a resistor and a simple oscilloscope. Maybe you have something for $60, you have an oscilloscope. So you can play with that. There's a lot of open source tooling. I believe there's a lot of parties and universities that have code available to do a lot of side channel part. Side channel is a lot of academic, I would say. Yeah, of course, I would recommend our equipment, but that is typically, yes, a beginner with a bit more budget. So we are very customizable, and what we typically see in our fields, we have different equipments. We have 50 different equipments, and it's like Lego. It is depending on what you want to do, you build. So every equipment that we have is has a certain function. So a little bit depending on what you want to do, I can perhaps help you even more if you let me know, or maybe message me what you would like to do. Maybe I can guide you more in that. So could you please elaborate difference SCA and FI attacks possible that can impact the data center environment? Yeah, so that's yeah, data centers I consider as vaults that are very hard protected, and yeah, so very hard to do local physical attack. Yeah, I think there could be some HSMs there. Maybe it starts with the authentication process. How do people get in? Assuming that someone wants to get in, there's some kind of cards or whatever. So maybe you want to bypass that mechanism first. Someone wants to illegally get access to that system. Then it could be, yeah, the malicious insider. So someone already gets in. Maybe he knows what kind of HSM or something that is being used there. A malicious insider could. There's actually, I didn't show that. We also did with a company next door, Fox IT. We showed how you can do Tempest-related side channel attack, where you record a bit stream or stream of VPN encrypted data, which for a certain time uses the same key. And while you record that for a minute, you will get a lot of samples of encrypted VPN data with the same key, and that you can something that you can then later on analyze. That's something I could also share later in some of my in a reference to you if you send me a message. Another thing is, of course, the HSM that is there. Maybe that you can investigate what it is, buy one offline, secondhand, eBay or whatever, and then try to find vulnerabilities there that could be software exploited and could be maybe remotely or planned with something with a malicious insider inside with a worm be manipulated without you knowing that. Yes, there's another. Can you please suggest some reverse engineering tools, especially for binary analysis, source code analysis? Yes, for reverse engineering, ourselves we do IDA. So it's yeah, what do you call that again? Reassembly. I forgot the right words, but IDA Pro is something definitely that we use. Source code analysis, there's a lot of players in the market like Synopsys, Coverity, Code Sonar. A lot of parties use that. We do as a lab do a lot of source code reviewing, but still we find so many vulnerabilities, especially on the embedded side. For me, these tools are good. They are generic tools. They have to focus on everything, any kind of language, any kind of standard, any kind of safety standard and code practice. They don't focus on security. for that, I would have to recommend our own tool, TrueCode, where we focus on C and C++ and look at logical fault injection and fuzzing vulnerabilities, either static and dynamic with. So yeah, happy to show you how our tool works on C and on embedded stuff if you're interested. I think I have 3 minutes left. So I will share you the presentation somewhere. And again, if you want to reach out to me, please feel free to do so. Anyway, thank you. Thank you too, guys. Thank you for attending. Please feel free to share this to everybody that you think should know more about fault injection.
So there is a lot of compliment for you, Bartek, in our chat box.
Thank you. Thank you. Yeah.
It was a very interesting session. Thank you so much.
So welcome.
So thank you.
Shall I stop sharing? Thank you.
Yes, thank you.
I'll stop sharing now.
So with this, we would like to conclude the webinar here. Thank you all participants for joining us. And thank you, Bartek, once again for such a wonderful session.
You're welcome. Thank you very much. Stay safe and hope we can meet each other soon, face to face.
Sure. Thank
Have a
you.
nice weekend. Bye-bye.
Bye-bye.